We will start in a few minutes. Um, my screen is visible, right? Like what I'm showing. Can anyone unmute or? Yeah. Okay. Okay. Um, okay. So it's. I think it's 5:31. Let's start around 5:33. Like 2 minutes more, and then so that. Um, okay, I think we can start now. It's 5:32 now. So, so I wanted to first discuss the plan for this week's lecture. So we are now currently conducting lecture 4, and tomorrow we would be having lecture 5, and next week onwards we would be heading. So we would be ending basic introductory machine learning by this week, and we'll be starting with probabilistic graphical models, which is the first part is Bayesian networks, which would be starting next week, or even like some part of it we can do it tomorrow also if one of them gets done earlier. So for this lecture I'm going to write mostly by hand, sort of, and so that it's easy to follow for all of you. So these two things, regularization and lasso and ridge regression. Regularization would be done today. Lasso and ridge regression probably would be done by today also. And this thing can go to Sunday, tomorrow's lecture. And if we have some time, we can also include some intro to um, like graphical models, like Bayesian networks for tomorrow's lecture. So this sort of thing, until this week, we majorly sort of worked on um like introductory ML, and that sets up the base ground for sort of to starting into the advanced stages of graphical models. So let us recap what we did last week. So we were discussing about like MLE. One was MLE, and which is maximum likelihood estimate, and the other one was MAP, which is maximum a priori. So we, if you remember from the lecture slides, what we discussed was the WMLE part, which is the weight vector that you sort of optimize over the loss function, had some expression as like this, like this: summation j yj minus w transpose xj whole square, and WMAP had argmin w, the same above expression as follows, and but an extra additional term as lambda by 2 whole square. And as we saw last week also, we sort of we sort of ended on this note, for the MAP estimate, the weight vector, we get an extra additional term, which is this lambda by 2 w, the norm of w square. And in case of WMLE, we just have a simple expression, which is the just the L2 loss objective function. And so um, we now come to the concept of regularization. You might have already heard something like overfitting of a ML model. So what is overfitting? Overfitting is basically when you actually train your model on a training set on that's such that, like, the model actually learns very well on the training set, but when it comes to your testing on a test set, it doesn't perform so well, because it sort of learns the patterns in the training data and sort of memorizes a lot on the training data. And when it comes to new test data, which is out of the blue, then it fails to sort of provide good predictions and all. So this term, which we are having here, is called a regularization term, um, and this is provided by our WMAP estimate. So this MAP estimation actually leads us to a regularized solution, as we saw. And um, uh, and for the case of overfitting, we know, which is like complex models, complex ML models can often lead to overfitting. Can lead to overfitting. Uh, Complex models, by complex models I mean like uh, a lot of weight parameters, like in current age of language models. You have like lots of billions of parameters and all, although they don't overfit, that's a different case. But there are many instances also. But traditional machine learning algorithms, if you have a lot of weight parameters and lot of uh, like a neural network, if you consider a neural network where you have a lot of neural nodes and lot of layers and all, and if you that actually increases the complexity of the model, and as a result that sort of leads to overfitting. So why do we need regulation? Regulation is basically we need because so that like this this error function, this entire thing is a error thing. So we want to modify this error by adding this extra additional term here, so that the complexity is actually penalized. So this extra additional term actually penalizes complexity. We'll see how it does that. So that's the thing. So I can write it more in a more sort of general fashion as this, um, that um, that loss of this regularized loss, I can denote it as this, over this W is equal to loss of the entire data set, which is the just the um, just the L2 loss that we saw, plus some lambda um, into some regularization function. Like, so lambda is just scaling sort of parameter. So this regulation function can be thought of as like W norm whole square by 2. So I'm just adding a general sort of definition here, so that it's easy to understand. And what do we mean by this so what what sort of like one probable function is W norm whole square by 2, we saw. The other case can be something like, um, so we can have different functions of W, like this W can actually be W whole square, or um, it can be just a norm of W, or it can be any other thing to the power k something or something like that. But the most popular ones are W whole square, and it's called L2 regularization. Why it's called L2? Because it has this like L2 norm, L2 norm. So by default, I'm not writing this two at in the subscript position, but it always defines, is always as of now, like in the previous notations also, we didn't use the subscript notation when we were writing a norm, but from now on we would write that subscript notation. But by default, if you find anything like this, it's basically an L2 norm. And so that means in the L2 space, you define this norm, or the Euclidean space or the L2 space. And so that means, like for example, I have x plus y as, but if I'm giving an example, this basically means x1 plus x2 all square plus y1, something like this, like the distance metric, for example, in the Euclidean distance setting. And similarly, for if I have this thing, which is a one norm or L1 norm, it's similar to the mod of the like ec- the Manhattan, it's popularly called the Manhattan distance, and this is called the Euclidean distance. Just a moment, I think someone is trying to enter. Um, okay. Okay, so yeah, so this is a Manhattan distance, and these are some popular sort of notions of regularization function. One is W whole square, which is this L2 thing, and one is W one norm, which is L1 norm. And these are the two popular choices. So the first one, it's called ridge regression. If we use L2 norm setting. The second one is called lasso, and these are the basic definitions of the two settings. And so, what do we mean here? So, um, like, so my objective function now for ridge regression becomes like W ridge, if I denote it by this notation, is argmin W. Um, so remember, like we actually, so I'm now using matrix notation. So we had previously something like this as the loss, yj minus w transpose xj whole square. Now, what I have now is I can use the matrix notation, which is this thing, xw minus y um, whole square, and this is again a L2 norm, as you can see, because we defined it as a L2 least square loss, or L2 loss. That's why it's in L2 space. Plus I add some lambda also, this thing, which is a L2 norm of the W weight vector, and it's hence it's called ridge regression. And we are adding this penalty term to balance the sort of the measure of the fit of the model that we are getting, as well, and also the trying to reduce the complexity of the model so that it um, uh, doesn't overfit. You can also represent it way differently here. One option is also, remember we discussed basis function, where uh, instead of x we transformed it to some phi of x, but phi was some function like we discussed like polynomial basis, um, and then we had like Gaussian basis. uh, so you can find those on the previous lecture slides or even the videos. So I can write this in the format, like for basis function as follows. It's arc mean w. um, I now have again, it's a matrix itself, so I can write it as, um, so instead of x I will now have phi here, um, and y. Other things remains the same, and I now have something like this. Now what I want to do is, so this is my objective function. This is my objective function, and I want to find the optimal value w for this thing. So, um, so this thing, let's denote this thing by L ridge, for example. Let's denote this thing as L ridge, and
I have one question here.
yeah.
Uh, uh, what is the basic significance of this regularization term? I mean, what is the basis by which you say that you add this additional term, it's going to take care of the overfitting?
Yeah. Okay, so let me show here. So the why am I saying this? Because if you see, I'm actually minimizing the loss. First of all, I'm minimizing the loss, but also I'm not sort of my sum of the weight vectors. I'm also trying to minimize the sum or the individual weights in itself. Um, so if you see by the objective function, so minimize the entire thing with respect to w. So obviously my loss is getting minimized, but an additional constant is that my w, I should not choose a w so that my loss gets minimized, such that it's sort of like it's too low or too high, in that sense. So I am constant I'm putting a constant on the range of w here, and that is how like sort of my complexity like goes. I can sort of balance out complexity here. So if I give you an example, So let's say I have a model, a highly complicated model like this, like w2 x square plus this is up till w10 x10, and now I have 10 weight vectors, 10 parameters here. And if I plot it now, it would be something like, if I plot it in terms of x here, it will be something like this, like a complex model, curved in terms of x. Now I want to minimize the loss for this function, if, let's say, and that means like, in that case, my w higher order terms like w8 or w9 or w10, because it's like a L2 loss, is basically like w1 whole square plus w2 whole square plus up till w10 whole square is my w this thing, and whole square. um, and since I'm actually minimizing this thing, trying to minimize this objective also, as a result, this higher order terms like w8 w9 w10 gets close to 0 in that case. And my selection of the optimal w's results in close to 0 for w8 w9 up to w10. And as a result, my model sort of now comes down to something like this: w0 w1x plus w2x squared plus some very small value of w, or like these are the optimal values, so I'm using a hat operator here: w zero point 0.1 into x cube plus and so on, and plus 0 plus 0 plus 0. So it goes, the model complexity goes down to x cube only, or x to the power 4 only, instead of x to the power 10. So that's how my complexity sort of reduces. Yeah.
So the is the idea of lambda is very similar to penalty function methods in optimization. I mean, I can choose the value of lambda that
Uh-huh.
can uh, more closely match the data. Is it that way?
Yeah, makes sense. Yeah, lambda in that sense, won't be. I mean, lambda in that sense, it's like a balancing parameter between how much in emphasis you want to give on the minimizing the loss or the minimizing the this penalty function. So if you have a very high lambda, lambda equal to uh, let's say 1 point something, or like 100 200 or something, you give very high emphasis on minimizing this thing. But if you give lambda close to 0, then this eventually this term actually gets very close to 0. So you are just left out with this thing only. So you're just minimizing that thing. So lambda actually acts as a balancing parameter, which we want, which thing you want to minimize. So if you want very rigidly to sort of balance model complexity, like you don't want very high model complexity, but you are okay with some way of fitting the model, you don't care too much about minimizing the loss, then you can choose a very high lambda. So because your focus is to sort of reduce the model complexity. But
So basically,
yeah,
you are saying it is a user-defined
yeah, it's a user
constant.
defined, you are not optimizing it, it's a user
Okay.
defined constant. Yeah.
Okay.
But there are applications where also you can, like, if you go into advanced complicated sort of if you want to design an advanced complicated like system where you also want this thing to be optimized, then those things can also be taken care of. But on a basic high level, like on a starting ground, lambda is assumed to be a user defined variable.
So to me, it appears that the W2 L2 norm appears like a constraint, and lambda is a Lagrange multiplier.
Yeah, you can think of it like this. Yeah, that's true. That's true. Yeah. Yeah. So I'm not introducing that here, but yeah, that's true. You can you can think of like only this loss, but lambda 2 equal to something, and if you add that as a Lagrange dual sort of, and then you have that. Yeah. Yeah, you're correct in that sense. Yeah. Yeah, so any other questions? So let us go ahead. So we define our ridge regression loss as follows. Now we want to find the optimal value of W star that actually minimizes this entire expression. And if you remember from last week, and also like how you sort of minimize a loss function is basically you set the gradient of the loss to ridge to 0, and what you get is so that means gradient of, obviously it's with respect to W, so gradient of this phi W minus whole square plus lambda W2, this entire thing you set it to 0. Now I want to simplify this expression. If you remember from last week, what we did was we can simplify it as follows. It can be simplified as phi transpose phi minus y, and now we have lambda whole square, and we apply this thing. And if I simplify it further, so it with respect to W here, so it would be 2 phi transpose y minus, I'm actually sort of skipping some steps here, but it's easy to see, plus 2 lambda W is equal to 0. And so W star is equal to um, so phi transpose phi plus lambda I, um, yeah, phi transpose phi my inverse. Yeah, so let me recheck once. Yeah, yeah. So if you see now, this is my expression for my optimal value of W star that I'm getting for ridge regression. Now, if you remember correctly, we when we only had when we didn't have this regulation thing, we just had L2 loss, um, and we sort of uh, took a derivative of it. Then in that case, our W star had this expression phi um, phi transpose phi inverse and phi transpose y. So now for this is for ridge, this like the original sort of expression, original L2 loss, only the L2 loss without the regulation part. So adding the regulation part actually adds me an extra sort of extra sort of this item here, this factor lambda I here, and so that means like since this is an inverse, so the W star in this case would be l- less than W star original. So W star ridge, the magnitude of it would be less than W star original for lambda equal to greater than equal to 0, greater than 0. So because I'm adding an extra in the numerator part, because it's a matrix notation, but if you think of it from a perspective of since it's an inverse, so my W original would always be higher value than W ridge. So this is exactly the same thing we discussed a few uh, seconds back about the complexity reduction. Like the higher order terms get reduced to 0. Um, for the original case, I would have W8, W9, and W10, which are non-zero values. But as I add a regularization thing, my weight vector, optimal weight vector, that magnitude would actually be less than the original thing, and in many cases, it might go to 0 also. So that's the idea. And now we want to show another property here. So one thing is that our expression for W star was phi ridge was phi transpose phi plus lambda I inverse phi transpose y. So one question that you might have is that what if this inverse doesn't exist all the time? Um, like uh, like for example, the matrix for a matrix A, um, we know like for it to have an inverse, my determinant needs to be non-zero for a inverse to exist. So how do we prove that this thing, because otherwise if this inverse doesn't exist, then this thing as a whole is invalid. So we need to prove some way first that this inverse phi transpose phi plus lambda I inverse exist. And for that, what we do is, so we define a theorem, sort of like a small theorem, which is a matrix X, which let's say it belongs to R n cross n. That is a that means like it's a n cross n matrix of real numbers, and it is positive definite. So we are introducing a new term here, which is positive definite. We will define that if and only if, um, for a vector v which is not equal to 0, I have v transpose xv greater than equal to 0. So if I have this thing, um, then if I satisfy this condition, then x is positive definite. And another theorem is, so this is theorem 1, and theorem 2, 2 is, um, if a is positive definite, then a is invertible also. So these are classic sort of like linear algebra proofs. I mean, I won't go into details here, but you can actually pick up any textbook on linear algebra, like Gilbert Strang's book, lecture, or anything.
Can we say that? Can we say that if the basis functions are linearly independent,
Mhm.
then phi transpose phi will be invertible?
The basics for, yeah, yeah, exactly, yeah.
And here you are adding phi transpose I, so that's not going to reduce the rank of the matrix.
Yeah, that's true. Yeah, yeah. But for rank, yeah, in that case also, like you can prove in an indirect way that the inverse exists. Yeah, that's also one way of seeing. Yeah. So I'm actually creating a simpler proof here so that, um, yeah. So I'm actually using two theorems here. Like one is this definition for positive definite, and if I, so my idea is that my x is actually, in case of x, I would actually put phi transpose phi plus lambda I, and my goal would be to show that phi transpose phi plus lambda I is actually a positive definite matrix. And if it's a positive definite matrix, then I'm done. I can just use theorem 2 to say that it's invertible. So yeah, the other way you mentioned also, like that also is possible, like in that. But yeah, I mean, you also, like we also need to sort of write it down, the other proof also. Yeah, so I'm actually following a simple proof here. So what I want to show is this thing, um, and I want to show that this thing is actually greater than equal to 0. And how do we show that? So we sort of expand this thing, like v transpose phi, and I actually multiply it here, and I have v transpose lambda I v, and which I get is, so if you see here, it's actually like uh, 5v transpose 5v. If you can see why I wrote this thing as 5v transpose, it gets inversed for the product, and it would be lambda, since I is a scalar, sort of like you can just have something like this, And now we can use the same principle for L2 square, since these two vectors are this, so I can just write it as this, and also for this as v whole square. And now this thing is a positive thing, this thing is also a positive thing, and lambda we already defined it as a positive thing. So for lambda greater than equal to 0, this thing is always equal to get is greater than equal to 0 if lambda is greater than equal to 0. But in many cases of lambda, obviously, uh, we don't want lambda to be negative because it doesn't make sense, um, because we are actually using a weighting, sort of like a balance mechanism to uh, balance either the entire L2 loss or the regularization penalty. So lambda greater than equal to 0, my expression actually comes out to be greater than equal to 0. And since this thing comes out to be greater than equal to 0, I can say like phi transpose phi plus lambda I um, inverse exist by theorem 2. So that's my that's a way to sort of see like why this inverse would always exist. Now I would go to the other part, which is L1 loss. So we discussed L2 loss quite detailed. Now what I will do is I will discuss L1 loss, and L1 loss is also the same. Instead of lambda 2 whole square as a penalty, I now have lambda 1 norm whole square as a penalty term. And the idea is that L1 loss actually provides. So what's actually like? Let us first define this. I think lambda one is actually. So let's say I have d parameters. I can have something like this, and in case of lambda two um, whole square, I have j equal to 1 to d wi whole square. And so in case of here in case of L1, I L1 actually provides me more sparser solution. So L1 actually provides me more sparse solutions. What do you mean by sparse? Sparse means that most w's are actually equal to 0. And it's again in the same analogy, but I won't go into too much detail. Like there are actually like good, like very in-depth analysis on sort of mathematical, theoretical, um, in-depth analysis on in different research papers and all that actually show this. But so since it's too much advanced, I'm not actually going through in this lecture. So that's the idea. Like L1 actually provides me most w's equal to 0. So if I have to have my model complexity to be very low, I can go prefer L1 than L2. But one caveat is that this thing, this arc mean, um, this loss L2, which we had a L2 loss plus this L1 thing as the regulation thing. Now, if you see this thing is actually not differentiable, because we know like mod x is not differentiable at x equal to 0, and that's one issue. And for tackling that, like we again, like there are many ways to tackle this. One is this concept of sub-differential and all. So sub-differential, again, like this is not in the scope of this lecture, but sub-differential is something like you sort of divide the area of this thing, of this curve, this y equal to mod x. So for x equal to 0, my differential would be dy by dx would be um, dx by dx, which is 1. And for x less than 0, it would be minus 1. And for x equal to 0, it would be actually, if you see w- here, like if I extend this lines, so this line actually is a tangent, is a gradient to this line, and this line is a gradient to this line. And so at x equal to 0, my differential would, I would define that subdifferential as follows. I define it as subdifferential ds of y at by dx at x equal to 0 is equal to some convex combination of lambda plus 1 plus 1 minus lambda, I think this, yeah, 1 minus lambda minus 1. So this 1 actually comes from ds by dx at x greater than equal to 0, and this minus 1 comes at ds by dx at x less than 0. So if you see, like, there are many possible tangents to x equal to 0. Like, one is this thing, one is this thing, one is this thing. So you actually take a combination of all um, possible sort of tangents to that, but it's bounded by this thing. It's bounded by these two lines, x equal to um, the differential equal to plus 1 and differential equal to minus 1. So that's the concept of subdifferential, but we won't go into too much detail. So that's one way to sort of actually convert a non-differentiable sort of function to a differentiable um, setting. So yeah, so um, um, before we progress further, like, any other questions you have, please feel free to let me know.
Yeah, regarding this, changing the discontinuity to one of continuous. So it essentially means you are adding a smoothing function, right?
uh, it- it's actually like not I mean, it's not regarding continuous continuity part, it's actually regarding the non-differentiability part. For smoothing, I mean, I think you were mentioning, like, for discrete functions, like, for example, if I have something like a box function and all, then in that case, like, there are many ways to actually smooth out this to get into a continuous space. But this is for a non-differentiable thing, which is continuous in nature, but it's not differentiable.
No, I'm just asking you that the slope is changing from one side to a negative to a positive side.
Mhm.
So it essentially means that you, at the point of x equals to 0, you make it 0, then
Mhm.
it just smoothens out locally.
But yeah, exactly, that's true. So you have, like, the original function is, sorry, let me. So the original function is something like this. Now the smoothed one can be like this thing, but has a tilt and goes like this because x equal to 0. But you're actually losing information, like, at x equal to 0 there are multiple sort of gradient directions. So at x equal to x less than equal to 0, my differential is equal to minus 1, and its direction is this thing. And at x equal to greater than 0, my differential is plus 1, its direction is this thing. But at x equal to 0, I can have multiple directions based upon, because it's a single point. So it is a single, if you have a single point, it's a multiple sort of directions you can go ahead. So what we are doing is that if you just do if you just smoothen out x equal to just the so such that the differential equal to 0, there is just one case of it. But there, you need to also consider the other cases also, so that actually gets done in subdifferential here, where you take a convex combination of this thing. So this means, like, it actually lies within the boundary of this thing. So this actually lies within the boundary of this thing, the differentiable at x equal to 0.
Okay, okay.
Yeah. Yeah, any other questions before we head on? I think we can also finish bias versus variance today, probably. And I think tomorrow we can start with probabilistic graphical models, first lecture on that. Okay, so now um, I want to present a Bayesian view of regularization. So what do I mean by that? So you want to present, like, Bayesian view of regularization. So so this function, I saw, we know that for map our thing was argmin w um, summation j yj minus w transpose xj whole square plus lambda into some function of w. I denote it as this thing. It can be L2 ridge regression and or L1 for lasso regression. Now this this function can be achieved via sort of like different like uh, it can be assumed like there can be many assumptions. One is like I can have a L2 loss, L2 norm for, and it can lead me to ridge regression. Otherwise it can be L1, it can lead me to lasso. So which, or there might be other options also. So which, how do we select this? So like for example, like we set w this thing is equal to, let's say, this thing. So we get an L2 regularized solution, L2 regularized solution, um, using if you remember, like we also for the L2 loss we also defined something like uh, a probabilistic way, which is, which was this thing plus some noise, where this noise actually comes up from some Gaussian parameters. So we provided a probabilistic viewpoint of the regulation thing, and so we are actually trying to combine this probabilistic viewpoint with the Bayesian view of regulation. So um, if we set this thing to this thing, we now get a L2 regularized solution for the linear regression problem. And if we have a Gaussian prior also, then that's the thing, like we saw, like if we had a Gaussian prior, minimizing the loss actually comes out to be an L2 loss. This is something we proved in the last few classes. So in the same way, for other like priors, like other distribution priors, there can be other things, like there can be this w can be set to other, like L1 norm, or maybe any other norms, or any other function of w, based upon the prior distribution of this noise parameter. So this is just a sort of like a high level thing which I'm trying to say here. So for example, if I have w equal to L1, so we saw for L2 we had a Gaussian prior in the noise thing. For L1, if we have this, which is the lasso thing, it it's subjected to a Laplace distribution prior. Um, Instead of a Gaussian prior, I now have a Laplace. So I've defined the sort of what is a Laplace function or Laplace distribution. So Laplace wi, I have two parameters mu and b. Just like it's just like Gaussian. So in Gaussian we had wi, um, mean and variance. Now I have some mean w, and b is also a variance here. I, for this thing I have this expression, exponential of minus wi mod of wi minus mu by b. And for Gaussian we had something like root 2 pi sigma um, exponential um, wi minus mu whole square by 2 sigma square. So similarly, for Laplace also we have something like this. And if we choose Laplace as the prior, um, then we get a L1 or lasso uh, as the regularized thing. So that's the, I think that's the end of regularization and L1 and lasso, like ridge versus lasso that we discussed. And if there are any questions, we can take it now, and we can probably head on to bias versus variance after this. If you have any questions, please let me know. Any questions?
Now, one question that I have is that a single value of lambda will fit all the data, or it can still happen that you determine the weights and try to predict the values for certain other data, then it may again show a different value of lambda that will match the, I mean,
Mhm.
particularly, how do you deal with outliers?
Mhm. Yeah, makes sense. Okay. Yeah, for the one sort of like data distribution, you are probably sort of hinting on data distribution. For outlier, I think the distribution from which they are coming actually doesn't fit the original test training data distribution, because they are outliers, like they don't fit the original patterns of the training data. So in that case, obviously for outlier and all, if we have a single lambda for that particular training set, and uh, for um, for this rich regression, um, for that I think, in the case of, if we have, let's say, like if we have like no outliers, so one single lambda value would do, like any sort of user specified lambda value. But in case of outliers, it might happen like my loss would actually get affected due to the outliers also, and some choice of lambda that can also hamper my sort of actual value of w, the original optimal value of w. So we need to choose like lambda also carefully, so that that also takes into account the outlier, as you were suggesting. So in that case, I think, like, obviously one way to would be to manually sort of check with some value of lambda, different values of lambda and all. The other would be to actually define another objective function, like a optimization problem, that actually tunes this value of lambda, this regularization parameter, based upon like the outlier detection. For example, you want the outlier to be very far away. You don't want the outlier to actually um, like sort of modify the come into the loss picture. Otherwise, if you have outliers in your loss, I mean, it would overshoot, and you would try to minimize that. So you can tune your lambda in such a way so that the outliers don't come into the loss, and that itself is a separate optimization problem. So you can think of it in that sense also. Yeah.
Sir,
Yeah.
the bias variance trade-off, like I had read it that it's important in machine learning. Could you say how is it like why is it that important in machine learning?
Yeah. So on a high level, so we haven't started yet, but on a high level, if I give you like a sort of the motivation for it. So one aspect of it is that, so in bias, what do we mean by bias? So let's say the for the linear regression problem, you want to fit a sort of line, obviously in the data. You want, for prediction purpose, you want to fit a line. So now there can be like many possible like fits for that particular model. Like it can be a one line, or it can be multiple other lines. So for example, let me draw you so that it's easy. So there can be like some line like this, or it can be some line like this, and you have data points like this, and you want to fit a line, the optimal line. And so bias would actually mean like how much sort of like how much does your model sort of sort of depend on your previous estimates of the fitting of the line. And the variance would be like, so if there are multiple lines, variance would be very high, because there are much more variation in the fitting, that can actually lead to you to a better prediction, or a better optimal thing. So there is this trade-off between bias and variance. Why this trade-off is that variance means that you are actually sort of taking a much more complicated, let's say, much more optimal sort of like predictor. But in the case of bias, you are actually going back to the original sort of like you're sticking to the mean of the all the sort of like predictions, not the
So
any of.
it's
Yeah,
like finding a balance.
yeah,
It's like finding the balance, and
yeah,
okay.
yeah. So I would actually be going through in a mathematical, from a mathematical perspective. I think that would be give you a much more better intuition, but on a high level, that's the
Okay.
idea, like sort of. Yeah.
Okay. So, sir, could we say like this that bias basically measures by like all the real world problems are there and it is measured in a very simplified model. So, like till now, that's what I understood.
uh, Bias is a very I didn't get it, like can you repeat once more?
I meant, sir, I'm trying to understand the definition. Like now, I'm
Okay,
trying to
okay.
understand if I explain it, what would I say in a sentence?
Oh, okay, okay. So bias would be like a variance. If I go by variance it first, so if you have multiple optimal predictors, you can fit a for fitting a line. So as I mentioned, so variance would be so the mean prediction, the mean predictor of all the optimal predictors, the variance would be defined as for a particular for a particular data set like this, and I have multiple prediction lines as this follows. My mean would be something like this, and my variance would be defined as for this line would be this minus this thing, this mean thing, so whole square of that. So expectation over my particular uh, particular estimator minus the mean of all the estimators, whole square would be my variance, and bias would be basically the uh, difference between the corresponding a particular estimator, let's say estimator 1, minus the mean of all the other estimators, the average of all the other estimator would be my bias. So that's the, in one sort of like on a high level, that's the definition.
Okay, sir. Thank you.
Yeah. So we are actually going through bias variance now. So let me open a new tab, and so that.
So one more question here. Uh, does this argument is valid only if the data is following a Gaussian distribution, and if it matches with any other distribution, then you need a different approach.
Not an approach. I mean, the choice of my choice of my regularization function. That's the, so if I choose a Gaussian prior, it results out in a ridge regression problem. My W2 like L2 norm whole square for my regulation penalty, and if I take a Laplace plier, it would be it turns out like it would be better to use L1 norm for that scenario. So in there might be other prior assumptions, like other prior distributions that we discussed last week, like beta distributions and all. So there might be other choices of correspond like one-to-one correspondence to the choice of regulation function in that scenario. Does that answer your query?
Yeah, yeah.
Okay. Yeah. So now we would be going through bias variance trade-off. So we first want to motivate what do we mean by that. Like so one aspect was, so we defined something called training error first. So what is training error? Training error is basically like the estimated predictor that I was mentioning. Let's say I have yi as my ground truth label for ith training instance, and g of xi is my predictor, which is the line sort of like which I mentioned. And what I want to do is I want to sum it up across all training instance, and you want to define a loss let's say L over yi and g of xi. So this is my output and this is my predictor, and we want to evaluate how good is the estimated predictor, like how good is this estimated predictor with respect to my ground truth. So this is one sort of measure, like one measure is this, like one measure of a model evaluation, like model performance evaluation.
Sir, I
And
didn't get it. Could you explain again?
yeah, so yi is basically a ground truth for the ith instance, and g of xi is actually the predictor. The g of xi you can think of as the thing that we discussed, like it's a w transpose xi, for example. And both this xi and yi actually belongs to, let's say, the training set, uh, training data set. And what I want is, I want to define a loss. So let's assume like there is a loss function. It can be an L2 loss or any other loss functions. And I define it as follows: like it's a loss of yi and g of xi, um, and I sum it up over all n instances, um, all the training instances, and each of xi yi belongs to dtrain. So that means my dtrain set is actually equal to n, because total training examples is actually n. And uh, so that's the idea. So is it uh, does that clear?
Yes, sir. So
Okay.
it's basically like a the nearest prediction kind of thing.
Yeah. So g of
Okay.
xi can be any predictor. uh, so based upon the choice of weights that you have, if you have an optimal weight that you had, like w star, and you sort of assign it here, then it's the optimal predictor. But any different choice of w can actually give you multiple predictors. So ga of xi is actually one of them, any one of them, just sort of yeah.
Okay, sir, got
So,
it.
so the
Yeah.
least square would be one of the commonly used loss functions.
Yeah, least squared would be one of the commonly used loss functions, like L2 loss, for example. Yeah, least squared or L2. Any. So yeah, so this is my training error, and I define it as this. Now I have another thing which is also, which is my test error, and that's also one measure. And test error is basically the same as this expression. Only difference is that my xi and yi would actually come from my test data set, and that's the thing. And so now I want to plot a plot here, so that it's is a classic sort of plot that we see. um, like I want to plot error versus model complexity. So the plot would be like, let me show. So my y-axis is my prediction, like say, so my y-axis is my prediction itself, prediction error. So I will just show what it means. A prediction error can be test error or training error. So I would have something like this. This is my complexity, and I'm drawing two curves here. One is this thing, and one is in a different sort of color. Plotting this. So red is actually my test error, and the black one is my training error. And this at this point, somewhat at this point, I have some model complexity, if you see, like my training error sort of decreases and my test error also decreases. But as I increase model complexity, my training error sort of my drops to close to zero, something sort of like almost close to zero. But my test error actually increases, and if you can see, like this is a classic case of overfitting. that I'm actually doing very well on my training data, and as a result my training error actually decreases as we increase model complexity. But once we have new test data out of the blue, it doesn't perform well and my test error sort of starts to increase all of a sudden. So this particular point actually is a very sweet spot, sort of I can stop my evaluation at that point itself. Yeah, any question?
Yeah, actually, how do you define the model complexity quantitatively to be plotted on the x-axis?
Haha, okay. So would be model complexity would be basically the parameter w, the dimension of it. So w, if you remember, is a d-dimensional vector. So this d, if I start to increase, that would actually mean my model complexity. So if you remember, it was like w0 plus w1 x plus w2 x square, something like this. If this is a model up to w10 x10. Now if I add something like w11 x11, there is a higher model complexity than this entire thing. I mean, um, up till w10, this model has a lower complexity than up till w11. So if I start increasing the dimension, then it's a higher model complexity. Yeah. So does that answer?
Yeah, basically, you are saying that you need to plot this training and testing error to really assess how many, what's the optimal dimension of D that needs to
Yeah.
be used.
Yeah. In a sense that, yeah. Yeah. So the optimal dimension of D would actually indicate my training error is also low and my test error is also low. Yeah. That's my like optimal model complexity. So if you know about things like if you have too many parameters, w is actually a parameter. If you have too many parameters, that actually indicates overfitting, or um, actually means that my model complexity is much more. If you think of neural from a neural network perspective, if you increase the depth of the neural network, that means if you keep on adding more layers to a neural network, then you essentially also add in more weight vectors also, like w also. So increasing the depth of the neural network basically means you're actually increasing the model complexity, and by default increasing the depth of the neural network actually also means you're actually increasing the number of weight parameters. So dimension of the weight parameters in that sense. So that's the idea. So that actually indicates the my model complexity. So that's a way to quantify like my model complexity. Yeah. So you'll now go to bias and variance definitions. Um, so bias, variance, and I define another thing which is called noise. And so just as we saw, like we had training error and test error. Um, these three notions like bias, variance, and noise are also like some sources, some error measures also. This can also be thought of some error measure, and these are actually the sources of my test error. I can say that why I say as sources of test error. I will just go define that in a moment. So this bias and variance, this errors actually depend upon the choice of the model, and um, and if I sort of give you a sort of example. Let's say I plot this thing. Now I have data points um, like this, for example, and so if you see, my true sort of function would be this thing, a curve thing like this. But my fitted hypothesis can be something like a prediction, g of x would be something like this, for example. It can be, uh, I'm just saying, like it can be something like this, or there might be other case also. It might also be something like this, or there are many multiple possibilities. Or like I'm actually not including all of them, but just to show like there are. multiple possibilities. So which sort of function do you want to sort of get, like which is the optimal prediction, like optimal predictor. So as you saw, like these are multiple functions, so one other can be like something like this also, a prediction line. So there are like total, I think, five lines that I fitted here. So my red is my true function, and all the other color lines are actually predictor function, like the g of xi thing, all the other colors. And now if I take the average of all the colored lines, or average of the colored lines actually means average of g of xi, average of g of xi, I indicate it as g bar x. So um, let's say not g of xi, let's say just g of x only. Over the entire training data, this thing is actually one particular predictor, like g1x for example can indicate the blue line. Can indicate the blue line. Let me show it as this, g1x. um, the green line can be g2 of x, another predictor. The yellow line can be um, uh, another predictor, like third predictor. And so g bar x is actually for this, in this scenario, is g1x plus g2x plus g3x by 3. um, so that's my uh, average g of x. And I want to model this thing. So in case of bias, what I mentioned was bias is actually the difference in measure between a particular predictor, like a sort of like a, just a moment. I think some issue is happening. Yeah. So bias is actually a particular predictor, like over the all the average thing. So that means I can define it as f of x, which is my f of x is actually, let's say, my true function, which is the red one, true function. I indicate it as f of x. So bias would, I would define bias as follows: is f of x minus g bar x. So that actually means my how much of a difference does the true function differ, or how much of a distance that does the true function deviation the true function has from the mean of all the predictors, all the sort of estimators, g1 or g2 or g3, the mean average of all the predictors, how much does that deviate from the true function. So that is defined by bias. And for variance, I I would define it as let's just write it here. It's a measure of deviation of actual true function from average of all estimators or predictors, like the prediction lines. And this g1, g2, g3, this can all be varied by varying the w parameter, values of the w parameter. And so I now go to variance here. So variance is defined by so variance is actually a measure of saying like how much does a particular uh, estimator, like for a particular estimator, uh, for a particular estimator, g of x for example, like g1 or g2 or something like that. Let's say I pick up g1x. uh, how much for a particular estimate g1 is, how the deviation from its mean, deviation from its uh, mean, or the mean is actually g bar x. So I would say something like g of x minus g of x bar whole square, and I take an expectation out of it. So it's actually a variance. If you see the see the definition here, the expectation of e over x minus e of x whole squared is actually the variance. So in the same way, I define my things variance here. So actually, all the I take all the estimators, uh, and I individually sort of take a difference with its mean and whole squared it, and sum it up across all the estimators. So that's my variance. The other thing is noise, which we discussed. So if you remember, we defined in the L2, in the, well, in the linear regression setting, I have something like yi equal to w transpose xi plus some error or noise. So this thing is an unavoidable error. Like, you can't actually, in many cases, you can't actually reduce this error to zero. So wi cannot be almost approximated to zero, because even if you have some choice of w, that actually does the best optimal value, in many cases my error cannot be actually uh, close to zero, because there is additional noise, and this noise come from the data set and all other factors. Data set mainly, like noise in the data set, like distribution noise and all, outlier and all. So that's the one of the cases. So now what we want to do is, we want to do a bias variance analysis in the regression setting. So let's say, I have this thing, so now I want to do is bias variance analysis in regression. So let's say I have my true function, which is f of x, um, true function f of x. No, let's say my true function is y. Um, True function is y, and this is actually my predictor. So I'm actually changing some notation here, just to actually stick to the original, uh, like the regression problem, plus some epsilon. So epsilon, actually we assumed it comes, let's say it comes from a Gaussian distribution. And what we now want is, say this is my function now, like my two underlying function y is actually my prediction plus some noise. And what we want obviously is that, I want to pick an estimator, gdxi. Let's say I'm sort of denoting it as this, gdxi, such that my summation over all the training instance, this thing is actually minimized over some w. So this is the minimization of the L2 loss that we saw, and gdxi can actually internally have some w transpose xi. And so I can actually write it as w transpose x for gd, for gdx. And so for gdxi would be w transpose xi. So we want to fit a line, so gdxi can be one of the fitting line that actually fits it, like it can act as an estimator. So for a new, let's say for a new test set, for example a test set, you now have a new test point x hat, which is a new test point. So in that case, y hat would be f of x hat plus some epsilon. uh, my question would be like, what is the expected test error, like what is the expected um, test error. That would mean like error, let's say x hat, I would have g of d x hat minus my original function y hat, and I take a whole square of it, because I'm taking it as a variance. Let's say I'm taking it as a variance of, as one of the measures of error. So what would be my not variance, actually this is just an error, actually this is just the error. So that just the L2 loss error, like the prediction minus the y hat whole square expectation on top of it. So this is my expected test error, and I want to why is called a test error, because my x hat is actually comes from my test set. And and so there are many possible sort of so many possible choices of g dx hat, because if I change my w parameter, I get a different predictor in that case. And if I get a different predictor, I get a different colored line, and based upon that I can calculate the bias and the variance. So now what I want to show is actually something like something this like so I have this expression y. Let's actually drop this d thing, just have g hexat only. I had just for the sake of this sake of usage in the notation. Let me have this. So let's actually go into detail about this. Let's actually sort of expand and see like what we get. So this actually would be, if I do just a whole square um, expansion, it would be plus y hat whole square minus 2g of x hat y hat. And since you probably know, like expectation of like expectation has linearity in expectation. So that means like expectation of a plus b is actually expectation of a plus expectation of b. So in that case I can actually rewrite this as follows: expectation of g of x hat whole square plus expectation of y hat whole square minus again I would have expectation of uh, g of x hat into y of y hat. And um, so so this thing I can actually since g of x hat and y hat are actually independent of each other, I can write it as a product of expectations, g of x hat and g of y sorry um, expectation of y hat. And I again have this thing, like I'm just writing repeating this thing again. And I have g of x hat whole square. So this is my expression now. And what I would do now is actually take this thing, expectation of g of x hat. I will just write it something like this. So expectation of if you know like let me do first show this. The variance of x is actually expectation of x square minus expectation of x whole square. I guess like everyone knows this. So um, that means expectation of x square is actually variance of x plus expectation of x. Sorry, I think expectation of x whole square. And as a result, I can actually do this for this also. So expectation of g of x hat whole square, I can also write it as variance of g of x hat plus expectation of g of x hat whole square. So variance of g of x hat, um, this thing, variance of g of x hat, I can write it as expectation of g of x hat minus g of x hat, the bar, the average of the g of x hats whole square. I guess this is clear, right? Like since I'm just expanding the definition of variance. And for this thing, uh, I can just have this thing only, because um, since expectation of whole square, so it's actually an average. This is an average symbol. Since it's an expectation of g of x hat, so g of x hat bar, and now I have a whole square on top of it, because originally I had a whole square on top of it. So if I just substitute this thing in, if I just substitute this entire thing in this value, yeah,
You must have g bar of x, right? Yeah.
uh, here you are saying
Yeah, you
no,
should have
because
e.
I'm actually, let me rewrite this thing. It was e of x hat and a whole square on top of it. So expectation of what g of x hat actually means g bar x hat, because expectation is actually an average or a mean.
Okay, okay,
Yeah.
okay.
Yeah. So I can just replace this entire thing by this at the top. What I now get is expectation of g of x hat minus g bar of x hat whole square plus g bar x hat whole square, plus I had expectation of y hat whole square, expectation of expression of y hat whole square, plus minus 2 of expectation of g of x hat and g of x hat, and expectation of y hat. So now what I would do is, so y hat y hat actually, like, let me actually write it in this sense. um, so expectation of y, now I actually pick this thing. So y hat, so if I pick this thing, it would be y hat whole square, would be again the same thing. I'm using the same use case I was above. Y hat minus expectation of y hat whole square plus expectation of y hat whole square. So I'm actually using the same concept here, like this thing. And if I have this, so what I would have now is, so for this thing e of y hat I can actually write, if you remember, y hat was actually f of x hat plus epsilon hat. So that would mean epsilon of f of x hat plus epsilon, so not epsilon hat, just epsilon, and it was epsilon. So this thing is actually equal to 0, because epsilon comes from Gaussian distribution with mean 0 and variance sigma square. So the mean 0 actually is the expectation. So this is 0, and this is a constant, doesn't depend upon the expectation. So I'll just have f of x hat plus 0. So just f of x hat. Um, is this clear, right? So yeah, so just a couple of steps I think we are left with, and then I think we can close this today's lecture. Um, so we now have e of y hat. We now have e of y hat as this thing. So I can write it as e of this thing, e of y hat whole square was um, e of y hat minus f of x hat whole square plus f of x hat whole square, because I'm just replacing the e of y hat by f of x hat. And now if I go back and replace it there, and sort of like use this and use this, and go back and replace it above. I'm actually writing the final expression here so that it's easy to sort of check. Final expression would be like I started with this expression, which was g of x hat minus y hat whole square. The final expression would be coming as g of x hat minus g of x hat whole square plus g of x hat minus f of x hat whole square plus this thing f of x hat. So I'm actually skipping some steps here so that like only one step I'm skipping here. So this was my variance. If you no, so this is actually my L2 loss. This is my L2 loss. This is my L2 loss. So this is my variance. If you see the pattern here, g of x hat minus g bar x hat, the entire whole square, and this is my bias, g bar x hat minus f of x hat. This is my bias. So this thing is actually equal to variance plus bias whole square, because I have a bias and then top of that whole square, plus this thing was y hat equal to f of x hat plus epsilon, and epsilon comes from 0 sigma squared comma distribution. So this thing is actually expectation of epsilon, this epsilon hat whole square. It was because this difference is actually epsilon and I'm taking whole square of it, and that actually comes out to be sigma square only. So this entire expression would be variance plus bias plus sigma square, the L2 loss. So I actually probably we have to um, uh, like sort of continue tomorrow, but I guess we can also sort of like repeat this derivation again tomorrow if it's needed. But the idea that I wanted to present is actually the loss function that I'm trying to minimize, the L2 loss. That thing can be decomposed into my variance plus the bias plus the sigma squared, which is the noise variance. And so if I want to minimize my L2 loss, I also want to minimize the variance and the bias and all. So my taking into account the measure of error like variance and bias, and I can actually sort of model the L2 loss. I can actually interpret the L2 loss in terms of the variance and the bias. So that's the idea why I wanted to share this. So I can also like go through this entire derivation again tomorrow, so that it's easy to like again to see, and then we can head on to Bayesian networks for probabilistic graphical models. So yeah, so I think we can conclude for today. So one thing before we go, so are you? So I've shared this handwritten notes actually also in the Google Groups chat. So I hope you are able to access them. Yeah, if you are not, you can just write me a mail personally, sort of, so that if it's not accessible, so we can continue again from for tomorrow, and we could revisit this thing again, and then we can continue to Bayesian uh, networks. I hope that's fine, and yeah, if you have any questions, please let me know in the email, and I think we can conclude for today. Yeah. Any questions before we end, or we can? Okay. I think then we can call it off for today, and we can start off tomorrow. Tomorrow is from 3:30, and yeah. Um, Thanks everyone. So let's meet tomorrow.